Find functions f and g so that f composed with g equals h. h of x equals absolute value of 6x plus 4. So we want h to be f composed with g. So what that means is that we want to be substituting a function g into a function f. So one function is inside of another function. So when I take a look at this particular example, I've got an absolute value, and inside that absolute value I've got 6x plus 4. So because that 6x plus 4 is on the inside, I'm going to let that be g. g of x is 6x plus 4. That's the inside function. And then on the outside, I have the absolute value, and that's what I'm going to let f be. So f of x is equal to the absolute value of x. So if we were to compose f composed with g of x, that's substituting g inside of f. G is 6x plus 4, and that will go inside our absolute value. Solve the following logarithmic equation. Log base 6 of x equals 2. For this particular logarithmic equation, I'm going to solve it by converting it to an exponential. When you have a logarithmic function, like a logarithmic equation, like y equals log base b of x, you can write the equivalent exponential equation by writing b to the y equals x. So I need to follow that same pattern with the log equation that I have. So the base is 6, the exponent is 2, and this expression equals what's inside the log. So now I've solved my logarithmic equation because 6 squared is 36. And with every log equation you should check because you can only take the log of positive values. So I'm substituting that 36 in for x, and you can see that I'm taking the log of a positive, so I'll keep that solution of x equals 36. Solve the following exponential equation. Express irrational solutions in exact form and as a decimal rounded to 3 decimal places. Our exponential equation is 5 to the x equals 9. The strategy I'm going to use for solving this log equation is to take the log of both sides. I'm going to use natural log on the left and natural log on the right. What this does is it allows me to use properties of logarithms, and one of the properties of logarithms, called the power rule, allows you to take the power and move it in front of the log. So this becomes x times natural log of 5 equals natural log of 9, and we're going to divide both sides by divide both sides by natural log of 5 to get x by itself. So this is what we call the exact solution, the exact form. And then we're going to type this in our calculator to get the approximation. So in the calculator, I'll use natural log of 9 divided by natural log of 5. And we want to round to 3 decimal places, so that's approximately 1.365. Find the amount that results from the given investment. $100 invested at 10% compounded quarterly after a period of 2 years. So first thing I notice here is a keyword, compounded quarterly. That's going to tell me which formula which compound interest formula to use. And we're going to use A equals P times 1 plus R over N to the NT. P is the principal, R is the interest rate, T is time, N is the number of compoundings in 1 year, and A is the amount. So for this example, the principal is $100. We're investing $100 at an interest rate of 10%. We're going to write that 10% in decimal form. We're going to be compounding quarterly, so that means 4 times a year. So N is 4 for a period of 2 years. So let's substitute these values into the formula. That's A equals 100 times 1 plus 0.01. Hold on, do I have that right? That's wrong. Let me fix that. So 10%, we move the decimal place 2 places, so that's 0.1. 0.1 over 2. 0.1 over 4, that's our N, to the 4 times 2. So we'll put that in our calculator. That's 100 times 1 plus 0.1 divided by 4 to the 4 times 2. So after 2 years, that $100 turns into $121.84. And I'm rounding to 2 decimal places because we're talking about money, so I rounded to the nearest cent. Find the vertex, focus, and directrix of the following parabola. Graph the equation x squared equals negative 12y. Before we work on this question, I want to show you just a few features of parabolas. So I have a picture of a parabola here, which is oriented vertically. And some of the key features are the vertex, which is right here, where the parabola changes from decreasing to increasing. Then on the inside of the parabola, we have the focus. And then on the other side, we have the directrix. We also have the axis of symmetry, which is running along through the focus and the vertex. And notice that that's perpendicular to the directrix. And we also have this latus rectum line segment, and that is passing through the focus and has 2 points that are on the parabola. We have the orientation that I'm showing you here is a parabola that faces up, but parabolas can also face down, left, right. Actually, you can orient the parabolas anyway, but in this class we're focusing on up, down, left, and right. So we have some equations here, and this first one with it oriented up, you have the squared on the x and a positive value on the other side of the equation. If you put a negative value on the other side of the equation like this one, your orientation is down. If the squared is on the y, you're going to be oriented horizontally, and in this case, because it's positive, to the right. And then when you put that negative on there, it orients it to the left. Now these are all with your vertex being at the origin, but you can move that vertex to any other position by shifting. So we have x minus 8 to shift it h units left or right, and y minus k to shift up or down. So now let's go back to our example. So what I want to know is the orientation of this parabola. So what I notice is that I have a squared on the x. That tells me that the parabola is going to be oriented either up or down. And then I notice this negative, and that negative tells me it's going to be oriented down. Now the reason why this is important to do first is because it's going to help you identify where the focus and the directrix will be. So with a down-facing parabola, the focus will be down from that vertex, and the directrix would be a horizontal line away from that parabola like this. So that's going to help me identify the location of these special features. I also noticed that in my equation, I don't have any values added or subtracted to x, and I don't have any values added or subtracted to y. So that means that my vertex is at the origin, which is 0, 0. So I know that the vertex of this parabola will be at 0, 0. A down-facing parabola will have this equation right here, the squared on the x, the negative attached to the y term, and this negative 4a is important to note. That value of a tells me the distance between the vertex and the focus, and also this distance as well, the distance between the vertex and the directrix. So I need to figure out that value of a. So I'm going to take negative 4a and set it equal to the coefficient on this y, which is negative 12. I'll divide both sides by negative 4 and get a equals 3. So now I know that my focus will be 3 down from that vertex, down because the orientation is down. So my focus is the ordered pair 0, negative 3. And my directrix will be 3 up from that vertex, and it's going to be a horizontal line. So that's going to be y equals 3 for my directrix. Then finally, the last thing I want to do is to graph this parabola, and it's very helpful to graph the parabola by finding the latus rectum points. It gives you a feeling for how wide the parabola will be. So the latus rectum points are going to fall along the same line as your focus. So I know that my focus is at 0, negative 3, and the y coordinates of my latus rectum points will be negative 3. So what I can do is take my equation, x squared equals negative 12y, and let y equal negative 3 so I can find those latus rectum points. So that gives me x squared equals negative 12 times negative 3. That's x squared equals 36. I can solve this by square rooting both sides. That gives me x equals plus or minus 6. So I have two ordered pairs for the latus rectum points. That's 6, negative 3, and negative 6, negative 3. I'll plot those latus rectum points. And now I can draw my parabola.